In this lesson, we're looking at the roots of complex numbers. So if we start by defining Demoivre's theorem again, we know that z to the power of n is equal to the modulus to the power of n cis n times the argument of any complex number in polar form. Roots of complex numbers is looking at this in reverse. So if we consider that we have z to the power of n, and it's already gone through this process and it's simplified into the modulus cis theta, so just a modulus and an argument, and we're trying to work out what z will be equal to, then we have to use roots in order to simplify this down. So really, this would be the same as saying z, that original complex number, will be the nth root of the modulus cis of the argument. Now, that's the same as saying that our modulus cis of the argument is raised to the power of 1 on n, and therefore we can say that it's a modulus to the power of 1 on n cis of theta over n. Right, so that will be our approach today. We're trying to find the roots of complex numbers. Now, it should be noted there, due to the periodic nature of complex numbers, there is going to be infinite solutions. However, due to the coterminal nature, there is only going to be n unique solutions. And that's what we're looking for. We're looking for the unique solutions. So we'll go through an example, and you'll see that this is pretty straightforward. So, EG1, we're looking at z to the power of 4 is equal to 1. We want you to solve over C. So we want to solve for complex solutions. So when we do this, the first thing to realize is that that 1, so z to the power of 4 is equal to 1 plus 0i. So we know there's only real, no imaginary there. And that 1 means we're starting at this point here. So that means our angle is 0, and our modulus will be 1. So we've got z to the power of 4 is equal to 1 cis 0. Because the complex number is sitting on this axis, and it doesn't matter where it was sitting, every rotation of 2 pi gives a coterminal solution. So we need to take that into account, where we go 0 plus 2 pi k for all values k, which are elements of a set of. Now, because it's raised to the power of 4, that means there will be 4 solutions. So we're going to use 0, 1, 2, and 3. And when we get to 4, we'll start getting the same solutions again. So we'll get that periodic nature applying. Okay, so to undo this power of 4, we take to the power of 1 on 4, or the 4th root. So we get z is equal to 1 to the power of 1 on 4, and then cis 0 plus 2 pi k over 4. And that leaves us with z is equal to 1 cis 2 pi k on 4. Now what we need to do, this is our solution. All we need to do is to sub in 0, 1, 2, and 3 to get our unique solutions. So for our first solution, when k is equal to 0, then we get z is equal to 1 cis 2 pi times 0 on 4, which is 1 cis 0. This is our first solution as z0. When k is equal to 1, we're having z1, so the second solution, 1 cis 2 pi times 1 on 4 gives us 1 cis pi on 2. When k is equal to 2, we get z2 is equal to 1 cis 2 pi times 2 on 4, to end up with 1 cis of pi. And then finally, when k equals 3, we get z3 is equal to 1 cis 2 pi times 3 on 4. We get 1 cis 3 pi on 2. And if we look at the coterminal angle within the domain, that is 1 cis negative pi on 2. Okay, so there's our four solutions. Now, if we look at k equals 4 as an extra, you'll see that Z4 is 1 cis 2 pi times 4 on 4 is the same as 1 cis 2 pi. And if we look at the coterminal solution there, that's the same as saying 1 cis 0. Now that's a solution that we've already covered. So this is a repeat of k equals 0. If we did k equals 5, we would get a repeat of k equals 1 and so on. So we have that periodic or infinite repetition of those same unique solutions. Now if we were to sketch this out on the Argand diagram, so real and imaginary, you will be able to see this pattern. So this first solution, 1 cis 0, second solution, 1 cis pi on 2, third solution, 1 cis pi, and then the fourth solution, 1 cis negative pi on 2. Can you see that there is an even split between these? So Z0, Z1, Z2, Z3, and the progression is a rotation of 90 degrees each time. So this approach will split the Argand diagram into even sections. Okay, so we'll look at a little bit, a question that's a little bit more complex. So example 2, we're looking at z to the power of 3 is equal to 1 plus I. Solve for z over c. So this time there's a little bit more in terms of putting the complex number into polar form before we solve. Okay, so we've got, if we look at a is equal to 1 plus I, we know the modulus of a is equal to square root of 1 squared plus 1 squared, which is square root of 2. The argument is in quadrant 1, so it's nice and easy. It's arctan of 1 on 1, which is pi on 4. So now when we set this up, and we've got z cubed is equal to, it's now root 2 cis pi on 4 plus 2 pi k. So we can't forget that 2 pi k because that considers all the coterminal solutions for all values k which are elements of a set of values 0, 1, and 2, because that covers the unique solutions, and after that we start repeating. Now when we isolate z, we think about square root of 2 is to the power of 1 half, to the power of 1/3 cis, and we've got 1/3 multiplied by pi on 4. Now if we simplify this to get a common denominator now, so this is going to be pi plus 8 pi k all on 4, then it makes it a bit easier. So that means we're looking at z is equal to 2 to the power of 1 on 6 cis pi plus 8 pi k all on 12. Okay, so now that we've got this represents all of the possible solutions. This is our general solution. We can look at substituting in with the given domain 0, 1, and 2. So k is equal to 0. We get z is equal to 2 to the power of 1 on 6 cis 0, so we end up with pi on 12. When k is equal to 1, we get z is equal to 2 to the power of 1 on 6 cis pi plus 8 pi will be 9 pi on 12. And then when k is equal to 2, we get z is equal to 2 to the power of 1 on 6 cis 2 times 8, which is 16 plus 1, is 17 pi on 12. Now we know that's gotten 5 into that next section. So it's gone that plus an extra 5. So this is 5 pi on 12. And this must be here, negative 7 pi on 12, which is a coterminal within the domain of complex numbers. So we can say this one's actually to the power of 1 on 6. This is negative 7 pi on 12. Okay, so there's our three solutions. If we had to sketch them on the Argand diagram, again, looking at real and imaginary. First one, the angle is pi on 12, and obviously the modulus length is at 2 to the power of 1 on 6. The argument for this next one is 9 pi on 12, so that means that there's 3 pi on 12 to that x-axis. And again, the modulus is to the power of 1 on 6. And then negative 7, which means that there's 5 here, 7 here, and the modulus is to the power of 1 on 6. Alright, so we should see that the angle between each of these is the same. So this is 8 pi on 12, this is 8 pi on 12, and if we go 9 subtract 1, this is 8 pi on 12 as well. So we have an equal angle between each of these solutions. And that's it. That's roots of complex numbers or roots of unity. Obviously, it's that process of undoing a complex number already raised to a power, utilizing Demois's and understanding of the periodic nature of complex numbers. Okay, that concludes the lesson. Thank you very much.